Hi, good morning. I'm very excited to be here. It's really empowering to see so many women data scientists. And also after hearing that the conference is also combined with Michal Sela Forum, it's even more exciting. So today I'm going to talk about a recommender system, which is a domain that I'm working on for many years in academia and industry. And I want to highlight some of the main challenges when conducting research in the field of recommender system. So recommender system, we meet recommender system in many of our online daily activities. When we shop online, entertainment, travel, social science, other entertainment, and news. Recommender system basically help users cope with the overload of information by learning the user preferences, model user preferences, and then matching items that suit those preferences. Recommender system provides the user with a ranked list of items or one next best items, but they also maximize systems or business KPIs. It is known that recommender systems do increase significantly business KPIs. So commonly, a recommender system maintain what we call a rating matrix, which is actually a log of the user interactions with the item. It could be explicit feedback, like when user provide positive or negative feedback, or what we call implicit feedback, when just we look at the behavior, the positive behavior of the user within the system, like click events or purchase and add to basket and so on. So basically, recommender system would try to fill in missing interactions. So if we will look at a simplistic problem setting, we have a set of users, a set of items, user history feedbacks on item, and then the recommender system would try to learn a model that would predict a preference or would provide a score for each user and item pair by trying to minimize the difference between the predicted and observed feedback. And then use this score to recommend items to the user. This is, of course, a very simplistic setting. There are more advanced settings like learning some ranking, pairwise or listwise ranking, or like involving more factors such as user context and more. So besides being so wide in industry, the recommender system have a very large research community, which is unique in being very, very applied. The recommender system community, the research community, is driven by industry and provides a lot of innovation to the industry. Commonly or typically, we publish at the ACM Rexis conference or at many other machine learning-based conferences like KDD, AAAI, and others, because at the end of the day, recommender system is a machine learning program. For example, in the last ACM conference, almost half of the papers were either in the industry track or research papers presented by industry. While a lot of innovation in the field comes from the academia to the industry. So I just want to highlight and tell you why I think recommender system is an interesting and challenging machine learning program, and I'll just mention a few aspects. First is the sparsity. The rating table is very, very sparse. It could get up to sparsity of 99%. For example, in a marketplace, in e-commerce, people would purchase or interact with a very, very small portion of the items that are offered in the system. That, of course, entails that the algorithm needs to learn from very small positive data. And then there's also issue of cold start. In many domains, the setting is very dynamic. Many of the items come to the system and many new items and new users. And that entails the need to learn out of distribution and to handle this cold start phenomena. And then, because user can interact with different types of formats of data, music, video, images, text. It is required to actually fuse different and rich data modalities into one model. And of course, there is a scale problem like what we have in eBay. Many domains in recommender system are actually a big data problem, but there is also need to provide very low latency response online, which is even more challenging. And then there is an issue of biases. And I'll talk more about biases later in this talk. So, when we want to start like a research project in industry or in academia, for example, to develop a new service or a new algorithm or to develop something innovative, or where then a need to improve some service or some algorithms, a common research flow in recommender system and also in other machine learning domain is based on first obtaining or collecting data, generate hypotheses, train models, evaluate model with iteration with many variants of the algorithm, evaluating the model with some accuracy offline metrics until we reach a set of best algorithms, while academia stops here and hoping that really while taking all kind of statistical measures and all kind of issues that will really assess the reliability of the model, what happens in industry, the industry takes the best algorithm into the online setting and evaluate the best algorithm with business KPI until it reaches the best algorithm, then would then go to production. Besides the difference in the online and offline setting in academia and industry, and where both actually want to have a good correlation between online and offline, there is another major difference in the way academia and industry conduct research. Academia actually wants to innovate and to develop new technology so that the algorithms are compared to the best state-of-the-art algorithm that exists. While in industry, what we care about is the performance of good models that will meet the business KPI. We could go with simple models that will do the job and will be easy to deploy. Having said that, usually new technology and innovative technologies that comes from academia would probably have more chance to boost the performance. But this is a different agenda between academia and industry. Having said all that, I would like to describe a recent study that we've done in our lab in Ben-Gurion University about recommender systems and highlight some of the challenges while doing this research and other researches. So I'm going to present a paper that we published in the recent ACM conference. It is a joint work of our students, Tzuf, Amit, and Oren Sar-Shalom, and Professor Mark Last. And it's about bundling, recommendation bundling. Bundling is actually a marketing strategy, a very effective marketing strategy, where we take a package of products and we price them and we offer them to the user while pricing them lower than the sum of independent prices. It is known to have benefits for the sellers and for the buyers. So during the years, we had some studies about bundle recommendation. We worked on identifying bundles, and we worked on dynamic pricing of bundles, personalized pricing. But today, what I describe is actually ranking bundles or recommending pre-identified or preset bundles. So the setting is that we have users and predefined bundles, and we try to give score for a bundle for every pair of bundle and users, and then provide top care recommendation based on this score. And when trying to think of what to innovate and how to boost the performance of bundle recommendation, here is an intuition that we wanted to evaluate. We thought that bundles or items are bundled for a reason. There is some context that the bundle creates. There must be some relation between the items within a bundle. And if we learn it and model it, we can then try to model the preference of the user towards the type of the bundle, not only toward each of the item, but toward the context of the bundle. Because most of the other works, what they did is just, taking the items, scoring them, and then doing some simple aggregation. But we thought that if we learn the latent relation between the items in the bundle, it could boost the performance. For example, a bundle could be a series of some items, a sequence of items. It could be like a complementary item for some major item, like complementary accessories for a phone. It could be like, it could represent some pricing policy or any other relationship between the items. So with this intuition, we thought, how would we learn it? How would we model it? And then, of course, we looked into the transformers and trying to model it with transformers. The way transformers would find relation between words in the sentence, we could find relation between items in a bundle. Of course, we then had to adapt. The transformer technology into our domain, and we had to look at how to integrate the user into the architecture. So the way we did it, we thought of two approaches to integrate the user model into our architecture. One was what we called early fusion, where we learn within the transformer the representation of the items and the user together with an early fusion approach. And the other was a late fusion, which first we learn the relation between the item and the bundle, and then we aggregate the user representation after that. The early fusion was significantly better in all the data sets that we experimented, but also here we had two types of architecture that we thought of. One was what we call concat, when we use the embedding of the user, concatenated for each user for each item, so that we have vectors of user item pair within each bundle. And the second one was to add the user as an additional item within the bundle. Here, the performance varied between different data sets, and it was not significant, not any of the architecture was better than another. We had some more innovation in this paper that you were welcome to read it. For example, we tried different aggregation methods. We also initialized the representation of the user and the item by applying collaborative filtering before pre-training it, before entering it into the transforming, using some collaborative filtering algorithm and some other very nice ideas. We used BPR loss. The BPR loss basically maximizes the difference between a score of a positive bundle and a negative bundle. It's like a pairwise ranking loss. And then we tried it on different data sets, on 3 data sets, of course, as in academia, public data sets, and that vary a lot in their size and in number of bundles and so on. And indeed, the results were very, very significantly better. The intuition was correct. And we used different accuracy methods, and the results were better for overall the baseline that we used. We used basic baselines like popularity and BPR, but also we used state-of-the-art in the field with graph neural networks and others. And yeah, the intuition worked, and because we use it on 3 data sets, we're pretty sure that this result would also, we hope that, but we're pretty sure that the result would also hold when deployed online. So now, after describing this research, and I said you're welcome to read more details about it, I would like to highlight some of the research challenges that are relevant for our research, but for any other research in recommender systems, and how researchers should handle it. I think it's relevant also for the academia and for industry as well when we do offline experiments. So the first idea is that we have to make sure, or to have high probability that offline studies will correlate with online study, we need to try to make sure that our experimental setting simulate reality as much as possible. Of course, it's never 100% the same, but it should simulate as much as possible. This is somehow relevant or very similar to what we have in the health domain or in medical research, when we want our retrospective studies to correlate with clinical trials. So a lot of literature actually is relevant for both domains. So the first thing to start with is, of course, the data. Okay, so basically in academia, you use just a public data set, and the data should reflect the problem as close as possible. Even in industry, sometimes you need to have a lot of actions to collect the right data, or if you want to launch a new service, you don't really have data. So what you do, if you don't have the exact same setting of the data, you need to have all kinds of reasonable assumptions. For example, in session-based recommendation, when we recommend based on the current session of the users, what we do, and we don't have indication of the end of the session, one reasonable assumption would be to look at the idle time of the user and then to set an indication of the end of the session. For example, here at our bundle problem, we had 3 data sets. One of the data sets had the real bundling factor, but also the pricing. Yeah, the packages were offered in a lower price. There was a real bundling factor there, but the other 2 data sets, one of playlists that people define, and one was books that people define as a set of books that they want to read. This didn't have the pricing factor, but still we thought that it would be reasonable that if we have the bundling factor, that the algorithm would still represent correctly our intuition. So this is the first thing. The second is the data split. When we look at a recommender system, basically we predict the users, the interaction or behavior of the user or the preference of the user based on the history of his activities. So the best way to split the data is by time, because otherwise we could have very easily data leakage. However, data stamps are not always available, and then people sometimes, you see papers that they do all kind of random splits where you should kind of question the results and try them really online to see if they hold in reality. But you should really look to split the data correctly. For example, if you split the data by users or by items, you just actually represent a scenario with called items or called user and not the real scenario that you want to solve. And then there's a big issue of biases in recommender system. Biases could be in the data, could be in the model, and then also while serving. And the bias is amplified when the user actually provides feedback on biased recommendation, and those biased data is going back to the next iteration of the system. So I'll try to talk about Some of the biases, mainly on the data biases, or the distribution of the training data is different from from our target data, and try to give you some hints of how to overcome it. So one main bias that is very common in recommender system is what we call an exposure bias. We have to remember that the data that we collect on recommender system from the user feedback is based on data that was collected based on some former recommender system that exposed to users only to a small portion of the original data. So for example, if the user really liked this item here that is kind of marked, but the system did not expose the user to this data, then we collect the data later as an implicit feedback data. The data doesn't have an interaction. This specific item doesn't have an interaction with this specific user, and we would consider it as a negative item. Okay, so this is an exposure data where actually the user generates behavior just on exposed items, but this deviates the distribution of the data that we collect. So another is a position bias, which is known also for the search engine settings, where user would click or would interact to item, even if they don't really like them, just because they ranked higher in the recommendation list. And then the next common bias in the data is a popularity. In recommender system setting, people would purchase or consume a small set of items that are very, very popular. And the other items won't get a chance to be exposed to the user because they're not popular. And this, all three biases that I described actually interact with each other, and there is a feedback loop that amplifies them in the system. So the research community and in industry were very concerned about biases, because when we have biases in offline, we cannot be sure that the system or that our algorithms would really perform well online or in the same way. So it affects recommendation accuracy, and then of course it hurts user and so on. So really the research community tries to come with a lot of solutions for this discussion and solution about this phenomena. And we see more and more paper about debiasing and how to handle bias specifically to the recommender system field. So there are three basic debiasing strategy. One is at the pre-process of the data, like reweighting or relabeling, by, for example, assigning weights to instances that modify the contribution. One recent trend is to try to work on what is called off-policy evaluation, where we take and we try to evaluate the learned policy with data from our target policy. This is something that is, there's like off-policy has different types of techniques, and industry recently tried to deploy it, but it's very, very still immature, and work is ongoing in this trend. And then we have a model-based, while modeling, and then a post-process, like evaluating with bias-aware evaluation, looking different metrics, and so on. So let me describe, just give you some hints on some method of debiasing. For example, if you remember the exposure bias, so you could reweight some of the instances heuristically. For example, a simple intuition would be that very popular items that are not interacted are probably more negative than non-popular items. And then another weighting strategy would be to take the propensity score. This is one example of the off-policy evaluation technique. And then sampling. We done sampling. We just select a portion of the data to work with. It could be based on random or heuristic, or with different sophisticated method of how to sample. We did a random sampling in our bundle recommendation. And there are also some, for the exposure bias, there are also some modeling where you model the exposure and the preferences. But of course, for all these sophisticated methods, you need to have information about your original algorithm. This is, of course, not relevant for academia. It doesn't have any information about the original recommended system that provided the feedback. In industry, you might have this information, but sometimes it's also challenging because the recommender system, in many situations, is an ensemble of different models. So I want to sum up now. So I see in academia a very good trend towards thinking of these issues and towards more theory-guided research to innovate in this domain and to try to make sure that offline studies would correlate with online study. So we do a different pre-process like we did with the sampling. We choose our positive evaluation procedures and metrics. We also conduct user studies to have more data or simulation with synthetic data. And we really try to do the best as possible and to provide innovation and technology that would really have good performance also in reality, but there's still always some blind spot that we could not be sure unless we could run, unless industry will run our algorithms online. And also, the academia is very, very busy with providing the biasing methods and research in the field. And for the industry now in the field of recommender system is bias aware, and they should follow academia for innovation and try to deploy, and they do it, the innovation in the field. And of course, collaboration is beneficial for both sides. And I hope I really convince you that recommender system is a challenging and interesting machine learning domain. And I would like to invite you to join our recommender system island community. I heard that we have a lot of communities, so we do have with Ila Weiss from Outbrain a new communities that you're welcome to join. And I thank you for listening, and we have like 2 minutes for question, I think. Thank you.
Very interesting, thank you. You spoke before about working both in academia and in the industry, and I wanted to ask you a general question of what do you find are the difference between working in academia and in the industry?
So, as I described, there is, first of all, a different agenda. While in academia, you just busy with innovation. We just want to have algorithms that would beat the performance of state-of-the-art in the field. In industry, you want to have the performance that would meet business KPI. And sometimes you take simple models. You don't really care about having the state-of-the-art, but you still, usually you do want to try those innovative algorithms because they would have the chance to beat the performance. But you look at considerations that you don't have in academia, like deployment and stuff like this, which is, academia doesn't have any. And also, when you work in industry, you have an access to great data, to real data. And in academia, you just have the data that the industry releases, which is distorted and it's not exactly, and then we have to make assumptions about the data. So, yeah. I think it's a big difference. But I think I do a lot of collaboration, industry and academia, with my students and also as myself, and I think collaboration is great. It just brings benefits to both sides. Okay, thank you very much for listening.